So as we discussed in the last video, our angle of twist equation looks super similar, right? TL over JG. It looks very, very similar to the equation that we saw for displacement in the axial loading section. So it should come as no surprise that we can solve statically indeterminate systems that are under torsion, just like we could with our load displacement equation for axial load, right? And the steps are going to be very similar, right? You're going to have a very, very similar approach where you're writing out the equilibrium equations, setting up a compatibility, and then using this relationship, right, our angle of twist relationship, to relate that movement to that torque, right? So what we're going to see is a very, very similar process, and it's much more similar to the compatibility method than it is to the flexibility method. It's also why I like the compatibility method better when we do axial load, because it primes you a little bit more for what we're doing here. But let's run through the basic steps of what we're going to do, kind of an outline of how you might approach statically indeterminate problems that are undergoing torsion, that have torque applied to them. Right, so you have, maybe some shaft or something stuck between two walls. Here's a wall, and here's the other wall, and it's subjected to these T1, T2 type of thing. So we can see that it's statically indeterminate. It's fixed between those two walls. And what's happening at those two walls is the reactions. Okay. Reaction T1, T2, reactions, let's call this TB and TA. So we have two different reactions here, but they're all acting along this same axis. Okay, we'll call this, the x-axis or something. So it kind of takes you back to statics when we're thinking about the setup for this, the equilibriums for this, of taking a moment about an axis, doing sum of moments. Right, so when we're looking at these problems, the first thing we're going to do is set up our equilibrium equation like in statics. But for torsion problems, it's always going to be the moment formula. You're always going to be taking a moment. So instead of the Fy, Fx forces, we're just looking at this moment. So we only have one known equation, but we have two unknowns for this fixed between the wall. We would need to come up with some other equation, some other example, and that's where our angle of twist really comes in. Right, so we can set up our equilibrium, take a sum of all of the moments. Here I'm using torque and moment interchangeably, right? Moment is just a torque that doesn't move, but they're the same, rooted in the same idea. So we're gonna set up our equilibrium, take a sum of all of our moments, which just means summing up the torques, right? Sum the torques that you have here. And then we're going to create our displacement relationships based on the geometry. So those compatibility. So for this miniature example here, if we're stuck between two walls, it means we know that that shaft can't actually rotate. So our angle of twist for this particular problem would be 0. Right, so we set up compatibility based on problem, geometry, displacement. You can think of it as displacement or the twist is a good way to think about it. We do the equilibriums, set up our compatibility based on what's actually going on in the problem, based on the problem geometry. And then we create that relationship of the angle that we find in this compatibility with this torque times length over polar moment of inertia times shear modulus of elasticity. This angle of twist relationship. So substitute in B equals TL over JG as needed, as appropriate for each section that you have in here. Determine your broken up sections, substitute in that relationship, and then you should be able to solve for your missing torques, right? Those reaction torques or anything else that you're needing. So solve for torque. So that's the basic outline. Those are our basic steps. But let's talk through it with an example problem. So for this example, we have a solid shaft with a diameter of 20 millimeters, and we want to find the reactions at the fixed supports of A and B. Right, so we have this rod here, it's jammed between walls A and B, has these two applied torques on it, one at 500 Newton meters, one 800 Newton meters, and we want to find those reactions. So our very first thing, if we kind of want to break this down and see what it looks like free body diagram style, then we can take this, here's our rod, and at each of those fixed supports, we're going to have a moment. I'm going to call this the torque at A and the torque at B. And I'm just making some assumption for their direction. I don't know what it is. And we'll leave it like that. And then include those applied moments that are on there, those torques. 800 Newton meters. And the way that we're going to approach these, right, is we'll kind of remember our moments from statics, imagining that this is the x-axis. I'm going to go ahead and do my equilibrium equation. So summing our moments, assuming counterclockwise is positive, summing our moments about that x-axis, right, about the rod here. So it's just that right-hand rule of which way is this going about this particular shaft. Because some of our moments is 0, and so all we're doing is adding the torques together, right? There's no applied forces. There's nothing really complex going on here. It's just some torques. So we've got 800 minus 500. Those are our two applied ones. Minus TA minus TB. Right, and that's just positive and negative convention for clockwise versus counterclockwise. So if we want, we could write this out as TA plus TB equals 300, if you wanted to simplify it. But that's our first step, right? Our first step is that free body diagram and writing out our equilibrium equation, our moment equation for all of these torques, what's going on here. And then our next step is our compatibility. Right? So our compatibility is just what is the actual angle of twist that is going on in this problem? How are things actually moving? And we'll see that because we're stuck between two walls, it is physically impossible for this rod to rotate. Even if we tried to rotate it, you might see some rotation in the middle, but it'll even back out as it gets to the end of each wall. Right? It is stuck to the walls. It cannot rotate. So what that tells us is that our angle of twist for our compatibility chunk here, pretend I spelled that right, compatibility, that our angle of twist is going to be 0, right? For the whole bar. But we know, as we learned in axial load, what we can do is break this guy up into sections. So every time we had that change in load or change in area or change in material, we would break it up into sections when we were doing our axial load. We can do that exact same thing here with torques. So I can look at this overall angle of twist is going to be the angle of twist of D with respect to A, right? This first segment here, plus the angle of twist of C with respect to D. So how C moves compared to D, that second section, and then that last section of B with respect to C. Right, and that gives us the overall bar, the overall angle of twist of B with respect to A. We can break it up into those sections and get this relationship equals 0. So that gives us our compatibility. So we've done our equilibrium chunk, our compatibility chunk, and our last one is our load displacement chunk, or our, there must be a better way to say it, a torque twist chunk, a torque angle chunk. Because what we're going to do is just substitute in our known torque times length over JG, this equation, our angle of twist equation, into this compatibility. Right, so maybe we should call it something cute, right? Something like the torque twist. The torque twist relationship. I'd like that. I think we should coin that. So our torque twist relationship here for D with respect to A is going to be, if we go ahead and chunk that out, let me chunk these out first. I don't want to do this whole equation. Let's chunk these out. I'm going to look at just the section, just section AD. Just section AD. Right, so we cut our thing right before we get to D, and what we see is we see that TA torque, and then we have the reaction torque here. So this is the torque in section DA. Right, if we look at our original thing, we include everything up to D. So we don't include that 500. So we can see in our section AD here is that the torque of DA is going to be the same as that reaction, right? The same as TA. We can go ahead and plug that into our displacement of D with respect to A is TA times the length of TA. The length of this section, is 0.3 meters. Whoops. .3 over J, my polar moment of inertia, I over 2 times R to the 4th, which I think it gave me a diameter of 20, so that tells me my radius is 0.01 meters. 0.01 meters. So 0.01 to the 4th power. And then I need G, which I do not have, but that's okay. I'm just going to leave it as G for now, because I have a feeling it'll take care of itself. They sometimes just like to take care of themselves. It doesn't tell me what the material actually is, it just says solid steel shaft, so it could be many different types of steel. Since I don't know, I'm not gonna guess. I'm just gonna move on and hope that that cancels out later. All right, so that was section DA. Now we'll look at section CD. All right, so we're looking at everything up until C. So this includes the torque at A, and it also includes this 500 Newton meter applied torque that we have at D. So that's this one here, 500 Newton meter applied torque. And then what we're solving for is whatever this cut is, right? So this cut through here, the torque in section CD. Torque in section CD. So I can do my little summation here, right? If I do an equilibrium for just this section, I get that the torque in CD is going to be TA plus 500. TA. Oh, did I draw the 500 the wrong way? I sure did. It's not going that way. I was wondering why it was a plus 500. That's why, it's because I drew it wrong. Right, TA and the 500 both go counterclockwise, or they both go clockwise. Our torque CD I assumed was counterclockwise. So TA plus 500. That makes a lot more sense. TA plus 500. I can set up my angle of twist of C with respect to D. Now I use that TA plus 500 as my torque term. TA plus 500 times the length of CD. The length of CD in the problem here is 1.5 meters. 0.5 over, again, it's the same area. Honestly, I don't know that I needed to write out this polar moment of inertia because I think it's the same for this whole beam, but I guess we'll find out. We'll find out when we get there. All right, last section BC. It goes up until not quite touching B. So it has the TA reaction, has the 500 Newton meters, and also includes that 800 Newton meters that's at C. And I think that is the right way. It goes counterclockwise. Yes, it does. Excellent. So now when I set this guy up, this is I don't want to draw it that way. I want to keep my sign convention. Keep my sign convention all the same for what I'm doing. All right, so TBC, that internal torque in section BC is going to be TA plus 500 minus 800, or TA minus 300. Simplify that. So that's going to give me an angle of twist of B with respect to C, TA minus 300 times the length of BC. So my length of BC is 0.2. 0.2. And then, okay, we're just going to put JG. I don't want to write it all out again. Because I can see when I plug all of these guys in to my equation, because this is set equal to 0, so when I actually pop all these into my compatibility here, J and G are all going to cancel out. Alright, so if I start plugging these guys in, I don't have a great place to do this, so we'll see if we can squeeze them in right underneath this compatibility up here. TA times 0.3, and that's over JG, plus TA plus 500 times 1.5, that's over JG, plus TA minus 300 times 0.2 equals 0. And again, because the JG term, the polar moment of inertia, shear modulus of elasticity, because those were in all three of these, and they're all the exact same material and radius, they all just cancel out. So we didn't need any of these. So that's fine. That's fine that we put it in, but it's great that we didn't really need it because we did not have a G. So now we can see that just with this compatibility equation, we can go ahead and solve for TA. So I can pop all of that into my calculator to solve for TA, and we get that TA is negative 345 Newton meters. So that means that the way that we had drawn TA, the way we assumed TA was moving in our free body diagram was incorrect. It's actually moving this way. But that's okay. We just denote it with the negative and move on with life, right? Go ahead and plug that guy into our initial equilibrium equation here to get our TB value of 645 Newton meters. So his direction is correct. And that's it, right? All we were doing was finding those reaction torques, finding those support reaction torques, using the same kind of layout, the same kind of steps that we did for statically indeterminate systems with axial loads. We set up our moment equilibrium, found a compatibility with the angles, and then substituted in that TL over JG relationship to find these torques. So for our last example here, we have a shaft made from a steel tube bonded to a brass core. If the torque is 250 foot-pounds, is applied at the end, determine the max shear stress for both the brass and the steel. Right, so you have the brass in the center there, the steel outer, we've got this torque applied, and we want to find out the maximum shear stress for each of them. So on its surface, it may be easy to trick yourself into thinking that this is not a statically indeterminate problem, but really what we're looking at here, if we were to draw our free body diagram or an approximation of one, is we have these dual cores. So for these dual cores, this torque is causing a torque in both the brass and the steel. Right, so this 250 foot-pound applied torque is causing a reaction in both the steel here, torque steel, and the brass. So if we set up an equilibrium equation for this, we're going to have some of our moments is 0 is going to be 250 minus the torque in the steel minus the torque in the brass. Or you can think about it like the torque in the brass plus the torque in the steel is going to give us 250 foot-pounds, right? They're each taking on a little bit of that torque as they're rotating. So even though it's not fixed on both ends, there is a rotation happening. It's still in equilibrium in the sense that both the torque and the steel have to move to counteract that moment, right? So that's how it's still a statically indeterminate problem, because we have two reaction torques that we don't know, that we need to find a compatibility equation for, right? Find a relationship to find what the torque in the steel and the torque in the brass is, so that then we can go back calculate our shear stress. So this is our first step, right? This is our equilibrium step. Then we're going to do our compatibility step. And if we look at the geometry, look at what's actually going on, because of this torque is causing that rotation, right? There is a twist that it's going through. It's initially sitting like this, but when this torque is applied, it goes through an angle of rotation here, right? This phi, this angle of twist. Possibly exaggerated for effect here, but that is going to be our angle of twist that's caused by this torque. Even though there are reactions here, they're reacting to that 250-pound torque, it's still twisting, right? It's not fixed on this end. It has the ability to twist. The key with this geometry is recognizing that the twist here is going to be exactly the same in the steel as it is in the brass, right? They both go through that exact same angle of twist because they're bonded together, right? So however much it turns, both of them are going to turn the same amount. They both twist that same amount. So this is our compatibility. Compatibility. Again, let's pretend like I spelled it right. With that compatibility equation, we can go and set up our torque twist. Right, so we can come down here, say, all right, I know that my angle of twist of my steel has to equal my angle of twist of my brass, just by the geometry of the problem. So we can come and start substituting things in, right? Torque steel times the length of steel over J steel, G steel equals torque brass, length brass over polar moment of inertia brass, G brass. So our torque steel and our torque brass, those are both components in our equation over here that we're looking for. We know that those are going to be our unknowns. So let's start filling everybody else in. We have our length steel and our length brass. And our length here is actually the same for both of them, right? It's this 4-foot length out. So because they're the exact same length, I'm going to go ahead and just cancel out this term. I'm not even going to bother to put in the 4 feet. You can if you want. I'm just going to cancel them out because I want to. Because I can, right? They're both the exact same. They're both 4 feet. My polar moment of inertia for steel and my polar moment of inertia for brass. Now, notice looking at our problem geometry, these are going to be different, right? They have different radii. Our steel is acting like a tube and our brass is acting like a solid rod. So they're going to have 2 different polar moments of inertia. And then, of course, the problem here gave us actually the steel modulus, shear modulus of elasticity for steel and for brass, which is 2 different numbers as it shows here, so we'll use the 2 different numbers. All right, let's go ahead and plug all that stuff in. So my torque steel going to be pi over 2. And then for my polar moment of inertia, remember it's acting like a tube here. We don't count the brass portion here. So it's pi over 2 times the outer radius to the 4th minus the inner radius to the 4th. So 1 to the 4th minus 0.5 to the 4th. And then times our shear modulus of elasticity for steel. 11.4 times, do I want to leave this in KSI? I think I will. Times 10 to the 3rd KSI. Okay, so I'm in inches. KSI is kips per square inch. I want to make sure I keep my units consistent. Torque for brass is going to be my polar moment of inertia. This time brass is a solid shaft, so that's R to the 4th. 0.5 to the 4th. And then for brass, G is 5.2. 5.2 times 10 to the 3rd KSI. So there we go. That gives me my second equation. I've got 2 equations, 2 unknowns. I can do some fancy magic in my calculator and solve those out. And I get, well, I will spare your lives the fun details of finding these, but our torque for the brass is 0.088 kip inches. And our torque for the steel is 2.91 kip inches. All right, now remember our question asks us to find the shear stress for these, but luckily we have our handy dandy shear stress equation that our max shear stress is going to be the torque times the outermost radius over that polar moment of inertia. So for the brass, that's going to be our 0.088 times the outer radius here is 0.5 for the brass, all over that polar moment of inertia that we just found. And that gives us a shear stress in the brass of 0.451 KSI. Do the same process for the steel. Torque times radius over polar moment of inertia. 2.91 times 1 is the outermost radius over pi over 2. 1 to the fourth minus 0.5 to the fourth. Punch it in the calculator and we get 1.977 KSI. So our steel is taking on a lot more stress than our brass. But that's kind of to be expected. He's the outer layer, right? He's got a lot higher shear modulus of elasticity. So he's got a higher strength. He can handle a little more stress. Right? So that's how we go through this process. That's how we find this these statically indeterminate problems. This is how we solve these statically indeterminate problems. Again, combining them with equations we already use, we already know, just going through our equilibrium, compatibility, and then putting those together with the angle of twist equation, our torque twist equation here, to find whatever it is we're looking for, the torques, so that we can find whatever other information we need.